And we talked about the discriminant in an earlier section. And the discriminant, it gives us how many zeros, roots, or intercepts that our graph can have. If your discriminant was positive, so greater than 0 is positive, notice you would have 2 real roots, right? It would actually hit the x-axis. If your discriminant is equal to 0, you have 1 repeated root. So like hits the x-axis and bounces off. So whenever it hits the x-axis and bounces off, this is called a repeated root. And then if the discriminant is negative, then there are no x-intercepts. Okay, we don't have imaginary values. Here we're talking about multiplicity, and multiplicity from the last section. I'm just going to go back. I think it was the next to the last problem, this one. Where we have the 0, remember the 0 is the x-intercept. You can rewrite a 0 as a linear factor, right? So if your 0 is in the form of c, because it's going to play a part in what we do today, then the linear factor is x minus c, right? So if the 0 is -6, right, I'm simply just going to, I'm sorry, this is x minus c. Right. So if our 0 is -6, I'm simply going to substitute -6 in this linear factor formulation. So it's x minus, because that minus is a part of our formula. I must multiply, I must substitute c as a -6. That double negative gives us a positive, so we have x plus 6, right? So we have x plus 6 as a linear factor. So notice once we write that out, we have x plus 6, which is actually -6 as a 0, and the multiplicity is simply the power on that linear factor, all right? So this is like a formal definition of multiplicity. It says the multiplicity of a 0 and a polynomial refers to, there's some handouts on the back, refers to the number of times a particular 0. And remember that 0 root solution all of these things are x-intercepts, right? The physical representation of those. So it's a factorization of the polynomial. It is essentially, it tells you how many times the corresponding linear factor is repeated. For example, if the polynomial has a factor of x minus a, and I was sort of using c in my example, raised to the power of 3, then x equal to a is a 0 with multiplicity 3. Now, as far as the problems are concerned, right, these problems are set up in the form of a graph versus that table chart we were looking at. So just keep in mind that the zeros are the x-intercepts, right? So I'm looking for every place that this graph's hit the x-axis, and it looks like it hits here, 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 and here, right? So I'm going to start with my leftmost 0 or x-intercept. So here the x-intercept is -3. The multiplicity, if the 0 or if the graph goes actually through that 0 to the opposite side, the multiplicity is 1, right? So here we have a 0 of -3. its multiplicity is 1.
The next one will be -2.
Right, the next 0 is -2. Since it goes through the x-intercept, it also has a multiplicity of 1. The next 0 is +3. It also has a multiplicity of 1, right? Because it goes through the x-axis. It doesn't bounce off. And we're gonna see what happens in a second when it bounces off. So the 0 is +3, the multiplicity is 1, and then that last 0 is 4, right? And it has a multiplicity of 1, right? So those are my solutions. It's a 0 at -3, its multiplicity is 1. So notice I'm writing these as true zeros, not as linear factors. We have a 0 at -2. It has a multiplicity of 1. 3 has a multiplicity of 1, and then 4 has a multiplicity of 1. So pretty much like the table method is just looking at a graph. All right, there is any questions about this? I would hate for you to miss this on the test. All right, here is a similar type problem. Right, we want to locate the zeros, which are the x-intercepts, and we also want to state the multiplicity. So as I go through and look for my x-intercepts for my zeros, it appears to be 1 at -4. There's also a 0 at -1. And then it looks like there's a 0 at +2. So I'm only looking for where the graph hits the x-axis, not the y-axis. So we have a 0 at -4. What's the multiplicity? If the graph hits and bounces off, that's that repeated root thing. So the multiplicity is actually 2. Right? If it hits it and goes through the x-axis, that's a multiplicity of 1. But if it bounces off, that's a multiplicity of 2. All right, for the repeated root. We have a 0 at -1, and it goes straight through the x-axis, so that has a multiplicity of 1. We also have a 0 at 2, and it goes straight through our x-axis, and that has a multiplicity of 1. So if it goes straight through the x-axis, the multiplicity is 1. If it bounces, then it has a multiplicity of 2. All right, so enough of the multiplicity stuff. Let's look at some end behavior. And for the end behavior graph, you're really looking at the ends of your graph, the arrowheads. Right? Now, we've kind of taken a look at algebra's common graphs before. So if you, just to kind of review, if you're dealing with a quadratic function, and it's also an even function, that's in the form y is equal to x squared. And if you were to graph y is equal to x squared, right, you would get a U-shaped graph. I'm just going to pull up the calculator for a second. All right, so if I were to graph, I'm just going to clear this out. Going to y equals, I'm going to put in x squared. I'm going to hit zoom in 6. Right, notice I get a U-shaped graph. This graph is even because the largest power is an even number. It's also even because when you graph an even function, both ends are going to do the same thing. They're either going to go up or they're either going to go down. Right? So one, you can tell if it's odd or even just based on the largest power. If that largest power is an even number, it's an even function. If it's an odd number, it's an odd function. We also talked about kind of reflecting stuff across the x-axis. So if I were to go into y equals, and let's say I make this negative x squared, and if I graph, notice that the graph reflects across the x-axis. Notice that both of my endpoints are still going in the same direction. All right. So if we have y is equal to negative x squared, it's like this. And then we're going to take a look at, let's say, a cubic equation, and this is odd. So I'm just going to look at y is equal to x cubed. All right, so notice I don't really have x squared and x and all of that. I'm only concentrating on that dominating term that we talked about. It's the largest variable raised to the largest power. Right? So if you were to graph this cubic function, I believe it's going to produce a S-shaped graph. So this is x raised to the third power. I'm going to do zoom in 6. And notice that if you take a look at these little pictures up here, notice that the middle parts of these graphs are dashed, right? So that means they can hit the x-axis, a few times, but the end behavior of these graphs has to be the same. If it's an odd function, notice that the largest power is an odd number. Notice that the ends are doing something different. One is going down and one is going up. So this falls to the left and it rises to the right. If we were to graph y is equal to negative x cubed, that should reflect our graph across the x-axis. Oops. So notice the graph looks like this. All right. So that's true for any graph whose largest power is an odd number, right? Okay, so with these two basic, these four basic graphs, the two basic curves, up here is the theory. So it's kind of split into two groups. You have an n where the n is odd, and the n is just your largest power. So this side says if you're dealing with an odd function, and I'm going to move this over. It says that if a is greater than 0, so that just means if your coefficient is positive, and if you're dealing with an odd power, then your graph will fall to the left and rise to the right. So that if you have an odd function with a positive coefficient, right? So just remember, coefficient is just the number part of your term. And since I don't actually see a number, it's an understood positive one. But the key thing is that coefficient has to be positive. The second little setup says if a is negative, so less than 0 means negative. And if your largest power is odd, then your graph is gonna rise to the left and it's going to fall to the right. That's always going to happen. Right? So just an example of that, let's say I'm going to go back to y equals, I'm going to put in x raised to the 5th power. It's an odd function. The coefficient of my term is a positive 1. So when I graph it, it should fall to the left and rise to the right. So if I hit graph, notice that it falls to the left and it rises to the right. If I, for example, change this to a negative x, let's raise it to the 7th power. It's still an odd function. The coefficient is negative, so that means when I graph this, it should rise to the left and it should fall to the right. Is everybody okay with that? Because if you look at this little theory stuff, it's got some funky stuff going on. It says as x approaches infinity, that means as x gets bigger and bigger and bigger, bigger and bigger, then your graph approaches infinity. So here's what that means. If this is on the x-axis, as x gets bigger and bigger and bigger, what is this graph doing? That y value is getting bigger and bigger and bigger, right? So that's kind of what this stuff is saying in a roundabout way. This says as x approaches negative infinity, that means as x gets smaller and smaller and smaller. So if this is on an x and a y axis and I'm going this way on x, then p of x, which is the y value, it gets smaller and smaller and smaller. But just to know that if it's positive, if the coefficient is positive, it's a odd power, it falls left, rises to the right. If it's an odd power, and if it's a negative exponent, it rises left and falls to the right. All right, now for the other setup, if n is even, right, this thing says if a is greater than 0, so that means if the coefficient is positive and your power is even, then your graph is gonna rise left and right. So even power and a positive coefficient. Right, again, that graph is gonna rise both to the left and right. If you have an even power and an odd coefficient, then your graph is gonna fall left and right. So that's an even power and a negative and a negative coefficient. All right, so that is what's called the end behavior of graphs. And I think there's some problems that deal with it. Okay, so I'm just trying to make sure I'm not skipping over anything. All right, so for this example, it says, what is the end behavior of the graph? So I'm not looking at this x-intercept stuff. I'm only looking at the end behavior. Even though it appears that this graph might stop, just remember that this thing has some arrowheads on it and it should keep on going. So as we look at the end behavior of this graph, it does what to the left? It like rises. So anything that rises is positive. So it's left positive, right? And then it's right negative. And so it like rises to the left and it falls to the right. Right. So I believe the answer choice here would be that third one. The next one says, is it odd or is it even? It's odd. What makes it odd? Right. The ends are doing something different. If they were going the same way, right, it would be an even function. But if one's going one way and the other going the opposite way, it has to be an odd function. All right. So that would be an odd function. All right, you will see something like that on the test. All right, for the next problem, it says select the graph of the polynomial function, note the intercept, the multiplicity, and end behavior. The only thing this problem really wants you to do is just match up the graph with the function. So my first thought would be to graph it on the calculator and then just match it up to the answer choices. I'll show you analytically how to do this, but I would first put this in the calculator and pick my answer choice based on a calculator graph. All right. So I'm going to go on to y equals. I'm going to clear out that function and I'm going to put it in exactly as I see it. Negative 2x. Okay, the parentheses mean multiplication. The calculator understands that x minus 3. I want to hit zoom and 6. Now, if you actually want to see the entire graph, I'm going to do a little zoom fit. I hit zoom. And if I scroll down to fit, which is zoom 0, it should fit the graph to the screen. So just based on this graph, which one of the answer choices would it possibly be? A, B, C, or D? I believe it's going to be D, right? Because this thing kind of rises to the left and it falls to the right. So I did a couple of tricks. First, I did zoom and 6. And if you notice how it graphs it, it does graph it this way. I can't actually see the end point, so then I did a zoom fit and it kind of stretched it out weird. Notice this thing is only going from -4 to +5. Well, maybe I should do that. I'm going to change the axis on my calculator to fit the axis on the screen, so that way the graph will look a little bit better. So here's how I want to do that. I want to go into, well, first you got to have your graph in the y equals. Next, I'm going to go to window. And in window, you see x minimum. That's the smallest value for x that you see on your graph. You have an x maximum. That's the positive or the largest value for x. You have a scale. The scale increments of your x-axis. Looks like this thing's going by ones. So the minimum value for x looks like -5. So make sure you hit the negative and not the minus, because it will give you an error. My maximum value for x is +5. My scale is 1. The minimum value for y is -25. The maximum value for y is +25. My scale is 5, right? 5, 10, 15, 20. Always leave your resolution at 1. And now if I correct, I should see something that looks a little bit better. Is everybody okay with that? I just put it in the calculator. You may or may not want to change the stuff up if you can kind of guess which one it is. That is how you would analytically do this problem. First off, I would set this equation equal to 0. All right, anything in standard form is set equal to 0. I would use the 0 factor property. I would set every factor equal to 0, right? And then I would just solve each one for x. So over here, I would divide both sides by -2, because the opposite of multiplying x by -2 is to divide by -2. If 0 is in the denominator, -2 is in the, 0 in the numerator, that's 0. Over here, I'm going to subtract 3. And over here, I'm going to add 3. Right. So these are the x-intercepts. 0, -3, and +3. So if I look at my graph, -3, 0, +3, that could be a candidate. I have the zeros, -3, 0, +3, that could be a candidate. This one doesn't have, it just has -3 and +3, right? It does not have 0 as an x-intercept. So I can kind of throw this one out. And then this one has -3, 0, and +3 as x-intercepts. Right? But which one of these is correct? Right. Well, since this thing is a cubic equation, because if you multiply all of this stuff together, somewhere down the line, you're going to get an x to the third power. The coefficient is negative. So if you have an odd function, the coefficient is negative, it should rise to the left and fall to the right. So this would be our, okay, but I would not want you to do that on the test. I would just prefer you to just put it in the calculator and match it up to the answer choices. All right, any questions about this one? All right, and I believe there's one last problem in this section. It says use a graph to write the formula of the polynomial function of the least degree. So what we're going to do here is we're going to write the zeros. We're going to then list the multiplicity. And then we're going to rewrite the zeros as linear equations along with the multiplicity and write it out as an equation. So what are the zeros for this graph? -2 and 0, right? Because that's where it hits the x-axis. So -2 is a 0 and 0 is a 0. What's the multiplicity at -2? 2, right? Because it bounces off. That's the repeated root. So the multiplicity is 2. What is the multiplicity at 0? Should be 1. So remember the 0 linear factor conversion. What is -2 as a 0? Well, my 0 is -2, and I'm just going to substitute -2 into this linear factor formula. So that's x minus a -2, which gives us x plus 2, right? What is 0 as a linear factor? Well, if I go up here to my linear factor conversion, it's x minus the 0, which is 0. And x minus 0 is what? X. Right. So my linear factor for -2 is x plus 2. The linear factor for 0 is x. Now I'm just going to put all of this together along with the multiplicity and write out the equation. So f of x is going to equal to x plus 2. And we're going to raise that to what power? The second power times what? X. And that x is raised to what power? The understood first power. So you don't have to multiply this stuff out. You can leave it in a factored form. So that resulting equation is x times the quantity x plus 2 squared. All right, any questions about this one, especially this 0 as a 0? That actually pops out x as a linear factor. All right, now in the next section, okay, we're going to deal with rational functions. And rational, it just means fraction. Right? So we're dealing with fractional polynomials where you have a fraction and, well, you have a polynomial in the numerator and you have a polynomial in the denominator, right? We talked about domain and range. The domain is the x coordinate, range is the y value. The x coordinate, which is the domain, that's also the input. That's the number you stick into the function. And y, which is the range, that's the output. Output. All right. We also talked about you can only consider a number a domain value. A number is a domain value if you substitute into the function and get an output. Right. We kind of talked about this. You can only use a number as a domain value if you stick it in the function and then it spits a number back. If you stick it in the function and then it spits you something back that's not a number, then you can't use that as a domain value. And it pops up with fractions because if 0 is in the numerator, doesn't really matter what number's in the denominator except for 0. The value is 0, right? So just to show that 0 over 100 is 0. 0 divided by -1,000 is still 0 because 0 is in the numerator. But if 0 is in the denominator, then it's what? Undefined. All right. So if I were to put in, let's say 100 divided by 0, the calculator doesn't like that too much. It says an error, you can't divide by 0. So that means that if you're dealing with fractions, you want to stay away from numbers that make the denominator equal 0, right? Because if the denominator equals 0, then you can't really use that number as a domain value because it spits out something that's not a real number, that's undefined. Right. So just kind of hold that in the back of our minds. All right, when you deal with rational functions, there are, am I missing something? Something called asymptotes. I thought I had another slide. And I'm just gonna pull up a picture. Okay, so I'll just put in asymptote. It's just to get an idea what an asymptote is. An asymptote is an imaginary line, it's not a part of your graph, that your graph comes closer and closer and closer to, but never actually touches the line. This would be an example of a vertical asymptote. Because the red line, this is the graph. This dashed line, that's asymptote. The graph gets closer and closer to it, but it never will ever touch it. If you're talking about vertical lines, bless you, vertical lines are in the form x is equal to c. Right, and I'm showing this because it's kind of revealing vertical and horizontal lines, because when you write out these asymptotes, you will have to write them out as equations. So here's an example. If it's a real rough sketch, 1, 2, 3, -1, -2, -3. If this were the graph, what would be the equation for that graph? Well, since it's vertical, it has to be in the form x equal to c. I'm just simply going to look at what value for x that line is drawn through. Since this line is drawn through x when it's 2, that's my equation, x equal to 2. For a horizontal line, they're in the form y equal to c. Oops, so let's just say this is, if this is the graph, what would be the equation? Well, since it's a horizontal line, it has to be y equal to something. So I'm just going to simply look at the graph and see what that y value is hitting. So it should be +2. So that would be, or have the equation y is equal to 2. So in a vertical line, there is no y variable, only an x. And in a horizontal line, there is no x variable, only a y. So if you have a vertical line that your graph hits, well, that your graph gets closer and closer to, but never actually touches, this is just an example of a vertical asymptote. Here is, okay, this one got all three on it. I don't think I can blow this up very well, but here is one. All right, so that's the vertical asymptote. This will be a horizontal asymptote. Notice how the graph gets closer and closer to the line, but never will touch. And this is called an oblique or a slant asymptote. It's a diagonal line that your graph gets closer to, but never will ever touch. All right, so those are asymptotes. This is how you, and I should have a picture of that on the notes. I don't know what happened to it. All right, so what we have here are some steps to find asymptotes, and I just call this an asymptote cheat sheet. And I would use this on the test. So it says to find the vertical asymptotes. So that's the vertical line. It says completely factor the numerator and the denominator. Then you set the denominator equal to 0 and you solve it. When you set the denominator equal to 0, what you are doing, you're just figuring out numbers that make the denominator equal 0. Therefore, you get something that's undefined, and that's what produces that vertical asymptote. So it's just 3 steps. Completely factor. Then you want to cancel if possible. Okay. Then you set your denominator equal to 0. Then you solve it, and then out pops the vertical asymptote. To find the horizontal asymptote, notice that you see some bullet points and then you see some checkpoints. The first thing you want to do here is you want to check to see if a horizontal asymptote exists. So notice there are no checkpoints for the first one, just bullet points on what to do. But for the next 2, you have to figure out if they exist first, and then if they exist, you would apply the steps. So for the horizontal asymptote, the first thing I'm going to do is look at this checkpoint. It says if the degree of the top is smaller than the degree of the bottom, then the horizontal asymptote is y equal to 0. So what does that mean? All right, well, let's take a look at this equation. F of x is 1 over x. What's the degree of the numerator? It's probably been a minute. This kind of goes back to the beginning algebra. The degree of the polynomial is just the largest power on the variable. The degree of any constant is 0. So like the degree of the numerator is going to be 0. So now technically I could attach a variable and an exponent. Because anything to the 0 power is 1. 1 times 1 is 1. That's not changing the value, but I can attach a variable and a power, and that power is the degree. So that's 0. The degree of any constant is 0. What's the degree of the denominator? Well, this x is understood to be raised to what power? The first power. So the degree of the denominator is 1. So would a horizontal asymptote exist for this? It says if the degree of the top is smaller than the degree of the bottom, which it is, then the horizontal asymptote is y equal to 0. All right, so that would be the horizontal asymptote for that. For this one, x plus 1, and I believe that's 2x squared plus 5x minus 3. What would be the degree for the numerator? Well, you simply want to look at the variable with the largest power. So this x has a power of 1. It's understood to be raised to the first power. So the degree is 1. What's the degree for the denominator? 2. So the degree of the top is smaller than the degree of the bottom. So the horizontal asymptote is going to be what? Y equals 0. Y equal to 0 is the x-axis. Right? That would be the equation for the x-axis. So that's what they mean when they talk about the degree stuff. It's just the power on the largest, was the largest power on the variable. And if you don't have a variable, only a constant, the degree is 0. All right, so it says that's the first checkpoint. The second one says if the degree of the top is bigger than the degree of the bottom, then there is no horizontal asymptote. If you're dealing with anything else, like if the degrees are the same, then you would apply these steps. It says divide each term by the variable factor of greatest degree. Then it says the equation of the asymptote is going to be in the form y equal to 8. And we're going to see examples of all of these. These are just the steps. To find an oblique asymptote, it says there's a checkpoint. It says if the degree of the numerator is 1 degree greater than the degree of the denominator, then and only then will an oblique asymptote exist. So the degree of the top has to be 1 degree greater than the degree for the bottom. If not, then there's no oblique asymptote. So just notice these last two have checkpoints, but the first one is just the steps to find the asymptote. All right, so let's take a look at an example. So they give us a rational function. We got a polynomial in a numerator, polynomial denominator. We have to find the x-intercept, the y-intercept, the horizontal asymptote, the vertical asymptote, and the slant asymptote. So how would we find the x-intercept?
First would be -5.
All right, so in order to find the x-intercept, we let y equal to 0 and solve for x, right? So remember, in function notation, y is equal to f of x. So I'm just going to rewrite this as 3x minus 5 over x plus 3 is equal to 0. I kind of flipped it around, but f of x is y, so I just let y equal to 0. And now we're going to solve it for x. Since I'm dealing with a fraction, the first thing you always want to do with fractions is get rid of the fraction. So you want to multiply both sides by the least common denominator. And whenever you're dealing with fractions, the first thing you should do is just kind of get rid of them. In this case, I'm going to multiply both sides by the least common denominator. So if I look on my left-hand side, I have a fraction. The denominator is x plus 3. If I look on my right-hand side, I have a 0, and the denominator is 1, right? The least common denominator between x plus 3 and 1 is going to be x plus 3. So I'm basically going to multiply both sides by the LCD, which is x plus 3. All right, so I'm going to multiply the left-hand side by x plus 3. And whatever you do to one side, you have to do the exact same thing to the other side. So on the right-hand side, the x plus 3's will cancel. So I'm left with 3x minus 5. Anything times 0 is 0. So now I just want to solve it for x. So I'm going to transpose -5. So I'm just simply going to move it across the equal sign and change its sign. So 3x is equal to 5. The opposite of multiplying x by 3 is to divide by 3. So if we divide both sides by 3, we get 5/3. So that first x-intercept when y was 0, we figured out that x was 5/3. All right, now we're asked to find the y-intercept. Okay, so find the y-intercept. We're gonna let x equal to 0 and solve for y. So y is equal to 3 times 0. So I'm just going over here to our equation and just substituting. Hold on to work it out. I didn't work these out before class. All right, 3 times 0. I'm just substituting x for 0. Minus 5. Okay, nothing to substitute there. Over 0 plus 3. So I believe I get negative 5/3. Right, because 3 times 0 is 0. I got negative 5. Right, a negative divided by a positive makes that entire number negative. Try to put both of those up. So the x-intercept let y equal to 0. Y-intercept let x equal to 0. And they wanted that as an ordered pair format. So there's 0, negative 5/3. Now this is not always going to happen. Like one number is positive, another number is negative. Always work them out. That not always happen. All right. Okay, there is one more. All right, it says the same. Well, here they're giving us a rational function. We're asked to find the domain, the y-intercept points, the x-intercept. Well, I'm skipping something. I'm sorry. Let's find the horizontal vertical. It's something we got to do today, so we're gonna stop that with this problem. All right, the horizontal asymptote. All right, so in order to find the horizontal asymptote, I'm going to refer back to the cheat sheet. And I'm going to look at these bullet points. So I want to look at the degrees of my numerator and denominator, right? So if we go back, what is the degree for the numerator? It's 1, right? You're just simply looking at that largest power on the variable. So the degree is 1. The degree of the denominator is also what? 1. So that means that a horizontal asymptote exists, right? Because if I go back to the checkpoints, it says if the top is smaller than the bottom, it's automatically y equal to 0. That's not the case. The second one says the top is bigger than the bottom. That's not the case. So now I'm actually going to apply these steps. All right. So the first step says divide each term by the variable factor of greatest degree. So here is what that means. Find the, I'm going to abbreviate that, horizontal asymptote. F of x is equal to 3x minus 5 over x plus 3. So what's the largest power on my variable x? It's 1, right? So that means that I want to divide everything by x to the first power. So like if my largest power was an x squared, I would divide everything by x squared. Doesn't matter if it's in the numerator, doesn't matter if it's in the denominator. You simply want to take the largest power and divide everything by. Now, this is the quick and easy part. If the numbers don't reduce evenly, then it's 0. So here's what I mean. 3x divided by x, will something cancel? The x's. So I get 3 minus. For this 5 over x, does anything cancel? This does not cancel to be an even number, a nice even number. That's 0. I'm going to explain why it's 0 in a second, but just the short part of it is if it doesn't simplify to give you a nice whole number, if you still got like some x's in the denominator, it's 0. In the denominator, x over x, that reduces down to what? 1, because anything over itself is 1. And then 3 over x, nothing reduces, so that is a 0. So then 3 over 1 is what? 3. This is the equation. F of x is equal to 3, which is the same thing as y equal to 3. So that means if you were to graph this, even though graphing is not a part of this problem, I'm going to put a set of parentheses, 3x plus 5, close that off. X plus 3, close that off. I'm going to do a zoom 6. And you'll notice when for the equation y is equal to 3, that would produce a horizontal asymptote. So that would be the equation for the horizontal asymptote, y equals 3. Now, that's not going to graph horizontal asymptotes, but it will graph vertical asymptotes. Any questions about finding the horizontal asymptote? First thing you should do is check the bullet points. If it satisfies everything, which this one did, then we would use the steps. Okay, we're gonna go through that one. Okay. So next, let's look at the vertical asymptote. All right. So the steps for the vertical asymptote, it just says completely factor the numerator, denominator, and cancel if possible. Set the denominator equal to 0 and solve. So find the vertical asymptote. Okay, same equation, 3x minus 5 over x plus 3. Can I factor the numerator or the denominator? Or like if I were to put a set of parentheses around this, can I factor out a greatest common factor? Not really, right? I can't factor that, make that 2 sets of parentheses, so that's already factored. If I look at my denominator, that 2 is already factored. I can't factor out a greatest common factor. It's not a square, so I can't use 2 sets of parentheses, so it's completely factored. I can't cancel anything. I can't cancel x's because this x is attached to this -5. I can't cancel x's. So from this point, I'm simply going to take the denominator, set it equal to 0, and solve it for x. So transpose 3, x is equal to -3. And if you look at the graph, This is that vertical asymptote. This is not actually a part of your line. This calculator is in what's called connect the dot mode. So it's going to take the point way up here and it's going to connect it to the point way down here, but that's not actually part of your graph. Right? If I were to go into this calculator thing, it's just like in connect the dot mode. If I were to change the mode, okay, make it smaller. All right. And now if I graph, notice that that little vertical line is gone. That's not actually part of your graph. I just took it out of the connected dot mode. But that would be the vertical asymptote. Now for the slant asymptote, again, if we go back to the checkpoints or to the steps, the first thing we want to do to check to see if one exists, and it says that the degree of the numerator has to be exactly 1 degree greater than the denominator. So if we look back at our problem, they both have the same degree, right? The degree at the top is 1, the degree at the bottom 1. So for this one, the slant asymptote does not exist because they both, the numerator and the denominator, both have the same degree. Now, just for example's sake, if this problem looks something like this, if you had x squared minus 5 divided by x plus 3, then a slant asymptote would exist because the degree at the top would be 1 degree greater than the degree at the bottom. But well, if they both were 2, you would still divide everything by x squared.